Okay, good morning. So last time we started part two from the chapter five, and we talked about amplitude. In this chapter, we talked about digital to analog convergence and analog to analog convergence. For digital to analog convergence, we study amplitude shift key, frequency shift key, phase shift key, and QAM modulation. Okay, and for the QBSK, we said that we'll use in-phase carrier and out-of-phase carrier. In this case, we will use four phases to represent our data. So R will be equal to 2, and we'll have four possible combinations of the bits or four levels, and then each signal element will include 2 bits. So each signal element will include 2 bits, and this is the implementation for QBSK. Then we talked about the constellation diagram, and we said that we can represent a different type of modulations using constellation diagram, where we put in phase carrier and out of phase carrier on the x-axis and y-axis, and represent each signal element by one point, and next to this point we'll put the value of this signal element, or how many bits included in this signal element. By the way, we name this point with this value symbol. So how many bits will put in one signal element? We name it symbol. Okay, and in this case, for each signal element will be represented by, and the angle will represent the phase. Okay, so by this constellation diagram, we can represent any modulation type. Okay, for example, amplitude shift key, we represent 0 and 1, so we have, and we change the amplitude. So for 0, we can put amplitude 0, and for 1, we put the amplitude is equal to 1, while if the phase is 0, we don't change the phase, we don't change the frequency, we only change the amplitude. So in the constellation diagram, we can represent the ASK as 2 points with different amplitude and 0 phase. The binary phase shift key, constant amplitude, so each one will have constant amplitude but with different phase, one at phase 0, and QBSK has 4 levels, so it should include 4 points in the constellation diagram because L equal to 4, and each point or each signal element have constant amplitude, so it's around side of the circle will have constant amplitude but different phases. So by this constellation diagram, we could present a different type of modulations. Okay, and then we talked about the general case, which is QAM modulation, that which is combination of the amplitude shift key and phase shift key. So in QAM modulation, we change both the amplitude and the phase. And the minimum bandwidth for the QAM modulation is the same bandwidth as amplitude shift key and frequency shift key. So within the same bandwidth, I can, using the QAM modulation, I can change the phase and the amplitude for different signal elements, so I can include large number of levels. So I can put more data, because at the end, number of bits per number of bits per signal element, which is R, and R equal to, look to L number of combinations, or L equal to the power R, different number of combinations. So if I increase number of bits inside the same signal element, I will have different combinations need to represent it by different signal elements. So for each combination, I will put certain amplitude and certain phase for each combination or for each level. So I can include by QAM modulation, I can change the amplitude and phase and increase the number of levels. So for example, for QAM, we have four signals. Increase this to 16 QAM. So 16 QAM, or the number before the QAM, is the number of levels. It's L. So I can increase to 16 QAM and put 16 points. And this value will have L equals 16, so I can put each point or each signal element at different amplitude at different phase. For example, these 2 points at the same phase but different amplitude. This is at different phase, this is at another phase, and so on. So I can change the phase as I want and the amplitude as I want to add more combination or increase L or increase the order, or name it order of the coil. I increase the order means that I increase number of bits inside each symbol. So how many bits here in each symbol or in each signal element? 4 exactly. And number of bits here are with R log 2 L, with L is 16. يبقى here I can send, for example, here 0000. So in one signal element, I send 4 bits directly instead of 1 bits in the amplitude shift key or frequency shift key. Okay. But now the last thing we stopped last time is now I can put the signal element in the constellation diagram as I want. I can change the amplitude and phase as I want. But which constellation diagram should have better performance? If I increase number of, and first I have two comparisons here. For the same the same يعني for the same L for the same modulation order, which is better to put it like this? Why؟ لا ما قلت ده remove دي دلوقتي. Yes, it has. At the receiver I transmit this. I transmit 0 with this amplitude and this phase. مثلا for example this is 0 0, this is 0 1, and transmit this with another phase and another amplitude. This is what I will send from the transmitter. But after passing this to the channel, what I will receive, this you can plot it. So if you use certain quad modulation and pass this quad modulation to the channel, instead of receiving this point, I will receive something like this. This point can be received here, can be here, can be here, can be here. And if I send مثلا 100 symbol or 100 signal elements, I can receive this in this shape. Not exactly in the same position. This is the IQ, but at the receiver side. This is at the transmitter side. But why I received it shifted? Receive the same symbol in the same position, like what I transmit. Why? يعني I transmit the symbol in this position. 1 point here and 1 point here. This point, I received it shifted. I can receive this point here, or here, or here, or here, or even here. Receive the same point in the same IQ. For example, if I transmit this with phase 45 and amplitude 1, I may receive it with at the receiver side. Maybe and the amplitude may be مثلا for example half. The received data can be shifted. the channel noise والattenuation الامبليتيود. It is amplitude 1, but as the receiver I can set it as amplitude and also some environment in the channel can change the phase. So the phase may change. So you just make thresholds. Here I'm using 4 coa, so make 2 thresholds. If I received any data here, it will decode them as 0, 0. If I received any point here, I will decode it as 0, 1. Okay. When I can decode it with الاكسس او شيفتد لو الامبليتيود قل significant او الفيز قل significant لدرجه ان البوينت دي I received it here. So in this case I will decode it as 1 1, which is wrong, which is error. Yes, here I consider I sent 0 0, but due to the channel so I received بدل ما كان الفيز 45 الفيز now مثلا minus 10. 1 1, which I while I am sending 0 0. طب الإيرور ده come from where? From the channel and from the space between points. ليه؟ consideration like this by C. مكتوب as a receiver side. هو ده السبيس so when I decrease the space between the point and the IQ or the error will increase. But if I decrease the spaces, I can benefit from increasing the number of levels. يعني this for 4 quad is very bad. Now L curve L L 16. By increase I got transmit so for the same modulation I will increase L I will have both advantage and disadvantage. The advantage, I will increase number of bit transmitted, so I will increase throughput and data rate and decrease the bandwidth. Or but on the other side, I will increase also probability of error. So which is better from this diagram? According to what I want. Which is better from error point of view? Now error point of view, that this is the better. This is the better. Okay. Any question? Now we'll move the second part بقى which is analog to analog convergence يعني all previous part كان digital to analog conversion. I have digital data 0 and 1s and I need to represent them by analog signal. Now I have already analog signal but I need to convert it to another analog signal. Why? Why we need analog to analog? بسبب الباندويث of the channel. And here, if I send this directly, it will be in the low frequency. So the bandwidth will be here. This is the original data. But I have more data I need to transmit. So I will not use only this bandwidth. I need to use all the bandwidths of the channel. So I need to shift this in the frequency to the bandpass channel. Instead of low channel or baseband channel, I will move it to a bandpass channel. So I need to shift it and send more data. This shift is analog to analog convergence. This is at the frequency F1. I need to shift it to frequency FC. So I need to change the bandwidth. So if I have band pass channel and not and I don't have low pass channel, I should make analog to analog conversion to send the data on the higher frequency. Okay, this is a signal at the baseband, the original data application, and now I need to transmit into the RF. We name it RF frequency or radio frequency or higher frequency, and it shifted to higher frequency or radio frequency. And this is the last part in the in the transmitter. Because the transmitter may have different tasks. The last task is to put the signal on the RF and transmit it directly. Last stage in any transmitter. Put the signal at the higher frequency and transmit this signal. So to make this shift or to make this analog to analog convergence, we have also three main modulation types. As we did in the analog, as we did in the digital to analog. Now in the analog to analog, we have also three modulation types, and these three modulations also depends on the characteristics of the analog signal. Amplitude modulation. So as we did in the digital to analog, we will change the amplitude. Frequency modulation will change the frequency, and phase modulation will change the phase. So these are the three main techniques for analog to analog convergence. The first one is amplitude modulation. Now I have the original data is analog, not digital like previous. And I will multiply this by a carrier frequency. So what's the frequency of the carrier frequency? FC. And now I have F1. This is the frequency of the original data. Now I need to shift it to FC. So I will multiply by another carrier frequency at FC. So the frequency of the carrier signal is FC. And the output from this multiplication is a new signal. So by this modulation, I could transmit with high frequency. So now I have high frequency signal, I have or high frequency analog signal, and I can decode it as a receiver by extracting the amplitude. So the receiver now will extract the amplitude in the decoding board. So the modulated signal is the envelope of the carrier. And how we can implement this? Just to have oscillator generate carrier frequency, carrier signal with frequency FC and multiply the original analog signal with the carrier signal. But again, what about the bandwidths? As we did in the digital to analog, the bandwidth will be around FC and now it will be 2B, will be the bandwidth of the original data. So now this bandwidth is, so the bandwidth of the amplitude modulation is double the bandwidth of the original signal. Okay? Any question? So the total bandwidth is 2B. So this amplitude modulation we used in the AM radio. So in the radio we have AM channels use this AM modulation. For example, in this case, for AM channels, we send so voice signal has a bandwidth 5 kilohertz. So the bandwidth for each channel will be I need to transmit voice with 5 kilohertz. That will be 10 mega. So I can put all the channels. Okay. Each channel will have 10 kilohertz bandwidth. So I can put different channel. And by tuning the AM radio, we just change the data. Yes, exactly. So I can use all the bandwidths. If I didn't make different carriers, so I can add more channels. This is modulation. For the phase bound modulation, same idea, but now I will change the phase of the signal according to the amplitude of the original data. So for I will change the frequency of the output signal based on the amplitude or based on the original analog signal. In this case, to change the frequency based on the amplitude, we used, like we did in the digital to analog, voltage control oscillator. This voltage control receives the voltage of the input signal, and based on the voltage of the input signal, generate increase or decrease the frequency of the generated data. Okay. But now what about the bandwidths? Bandwidth will be 2 1 plus b multiplied by the bandwidth of the original signal. So for the AM it will 2b direct. Now it will be 2 plus 1 plus b. B is a constant depending on the hardware of the actual implementation, and b is the original bandwidth. So as we did in the digital to analog, in the AFM, we always increase the bandwidth because we have multiple frequency now. We change frequency. So we have our central frequency, but we change the frequency around the central frequency to represent the original data. So I change the frequency. We need more bandwidths to represent the different frequency I can use to represent the data. So in this case, the bandwidth will increase. Will be 1 plus beta 2 1 plus beta multiplied by b. Will beta usually around 4 or 5. Okay, right. The same بقى for our radio بقى. We have now ال FM radio. So in FM radio, I will represent the data. I will give the data high quality for the FM. The quality of the voice will be better if you compare between AM channel and FM channel. Always the FM have high quality or better quality than the AM. So I will generate the data with higher bandwidth. So the original data will have 15 kilohertz bandwidth. And if I consider L beta equal to 4, in this case, I will represent each channel by 200 kilohertz. Eight megahertz to 108 megahertz. But now I need more bandwidth to represent the data. Okay? So now what's the advantage between the AM and the FM? techniques compare between them. Okay. This no station دي what is the advantage of this no station? What's the disadvantage? يعني waste of the bandwidth. So I lost some bandwidth here. And also what about the bandwidth? For the same 2 1 plus beta p now. So we use more bandwidth for the FM. But what's the advantage of FM? High quality. Why? Yes, exactly. Because the amplitude modulation, as we said in the amplitude shift key, to the noise of the channel. Because the noise of the channel or impairment of the channel always change the amplitude. So once it changes the amplitude significantly, so it will affect significantly. So it's hard for the channel to change the frequency. The channel may change the frequency, but with less amount compared to the amplitude. And this is clear if we if we use the AM channel and FM channel, always the AM channel has very bad quality, but the FM channel always have high quality because it uses frequency modulation, not the amplitude modulation. So the disadvantage is waste of the bandwidth and increase the bandwidth, but the advantage is better quality, less sensitive to the channel environment. Okay, any question? Last one is the phase modulation. Phase modulation, the same idea, but now I will change the phase of the signal according to the received data or the input data. And to get the phase of the signal, I will, for the implementation, I will generate an input signal and I will pass it by differentiator. I will take the differentiator to generate the phase بقى, not the amplitude now. And the output of this differentiator will be passed through the frequency, the voltage control oscillator. So now I will change the phase of the signal instead of the frequency. And the bandwidth will be also 2 1 plus p multiplied by the original bandwidth. But now the value of beta is less than the value of beta for the frequency. Beta between 2 and 5, here beta is lower, between 1 and 3. So the bandwidth will be less in the phase modulation. So the phase modulation will consume less bandwidth compared to the frequency modulation. And I will only change the phase according to the original data, and this is the implementation of the phase modulation. Okay, any question? Now it says last quiz one نخش على two. Any question? Okay, we still have some time, so we can run some examples.